Cool. Okay, so so this will go. What we'll go through today then together is the test summary and those questions on the back that summarise the unit. So integration test Thursday, 50 minutes, 40 marks. Quite short, sharp, shiny test. As we've said, it's a short unit. You get your calculator. You can bring a cheat sheet, and you can bring the formula sheet that you've been provided with. Again, you bring it. Up to you to bring that one. Okay, as far as the content goes, it's all of Chapter 7. So only the skills that we develop in Chapter 7. As far as the skills checklist goes, we've got evaluating indefinite integrals. We've got evaluating definite integrals using the fundamental theorem of calculus. Determining area under the curve and between functions. Okay, so all of those are method skills, except we take it a bit further with some spec techniques. And then the last one is really where the spec stuff comes in, is determining the volume of solids that we rotate around the x-axis and the y-axis. Now, when we're rotating around the y-axis, that does require a bit of knowledge from functions, about inverse functions and so forth. As far as revision resources go, I've given you tests 2020 through to 2023. There's also 17, 18, 19. Very happy to print them for you at any stage. All of the work solutions are on the OneDrive. You've got the review sets, so Chapter 7A and 7B review sets. They're a good starting point as well as, no one grabbed the exam booklet. Oh, integration exam questions. Now, so like I've given you a number, I've got, I think Jack's got one already. I've given you a number of exam question booklets, right? And we're just really trying to focus on the skill that we're testing. And so like this one's dedicated to the integration unit. However, because of the nature of some of the integration questions, some of it does go a little bit beyond the scope of what you need for this test, okay? But it is still skills that will pop up later in Year 12 spec. So like when we've done implicit differentiation and when we're revising and we're looking at functions and relations and so forth. That being said, it's definitely a resource to look at. And probably the majority of it we should know how to do at this stage. The only thing you don't need to know how to do is something called implicit differentiation. So that's listed in some of those questions. You can either skip that part or just leave that question if you're going to use that. So they're the revision resources. Any questions at this stage about the test on Thursday? Very good. Okay, so let's get into our review here then. So we've got question 1A, and we've got a definite integral to perform. We have the integral from 1 to the square root of 3, or 3 on top of 1 plus x squared, with regards to x. So I'd just be looking straight at our formulas, either from our notes book or from the textbook. And I'm looking at the form that it takes, and I'm going, that's one of the inverse trig functions. That's from exercise 7b. So if I flick to that, 7b, integrating to the inverse trig functions, and we can see we've got 1 on top of 1 plus x squared goes to arctan of x. So I'm going to pull that 3 out front. We have the integral from 1 to root 3 of 1 on top of 1 plus x squared, and now this goes to arctan of x. Now, we could just type that into our calculator. However, most of the time with these questions it says solve this definite integral exactly. So that means we need to perform all of the steps of the fundamental theorem of calculus. The first step is the statement. The second step is going to be the integration. So we know that 1 on top of 1 plus x squared goes to arctan of x plus c. We don't need plus c because it's a definite integral, it has boundaries. Okay, so we have the integral statement, we have the antiderivative. Then we're going to plug in our upper and lower bounds. Arctan of root 3, take arctan of 1. Simplify those. Now the way we're going to simplify arctan is we're just going to type in shift tan root 3 in our calculator, or you can look at the unit circle to discover the angle for which it's true, if your unit circle has tan values on it. So this gives me pi on 3, and this gives me pi on 4, and so we're left with 3 pi on 4, take pi on 3, take pi on 4 times 3. Whoop. got pi on 4. Okay, and they're all of the steps that you're required for your answer. If you type this into your calculator, it will spit out pi on 4 for you. So that's going to be some of the opening questions. In B here, let's move on to B. We have the integral from 0 to 1 of x squared e to the 3x, e to the x to the 3 plus 1 with regards to x. Now, if you've done the exercise 7C on substitution, now we did this at the end of last term, so it was a few weeks ago. But what we're doing is we're looking at that and going, these functions, like I can see a relationship between them such that this is some form of the derivative of this function. I'm going, that's x to the 3, that's x squared, so this is a derivative of it. So what we're going to do is we're going to let u equal x to the 3 plus 1. Then what we'll have is that du on dx is equal to 3x squared. Okay, if we differentiate u, we'll get 3x squared. And so from this relationship, we can have, therefore, x squared is equal to a third of du on dx. Okay, so I'm taking this equation and just dividing both sides by 3 to get something in terms of x squared. Now, I'm going to restate our integral all in terms of u and du on dx. So what we have is we have the integral from 0 to 1 of, that's going to become a third du on dx. Okay, and this is e to the power of u. And then we have, with regards to x, now, we'll simplify it before we integrate it. If I'm going to multiply all this out, I've got dx at the bottom and dx at the top, they're going to cancel. And so what we're left with, I'll even pull the third out the front. Just always makes the fundamental theorem of calculus that tiny bit simpler. We have e to the power of u with regards to u. Now the integral of e to the x with regards to x is just e to the x. The integral of e to the u with regards to u is just going to be e to the u from 0 to 1. Now we can substitute u back in, which is x to the 3 plus 1. And then we'll plug in our 1 and our 3. I'm going to need a little bit more room, so I'll come up here. So we'll have a third e to the power of 1 plus 1. Take e to the power of 1. So we're left with a third e squared take e.
Isn't that a third e squared take 1? Because it's, oh wait, no, because it's to the power of 1.
Yeah, so that's e to the 0, yeah. Good. Yeah. Cool. Okay, so this is a good example of like an exact answer. Like if you type this into your calculator, it's going to spit out a decimal. So if we want to find an exact answer, we do have to perform the fundamental theorem of calculus. We're using substitution, we're arriving at our answer. However, one way we can check that we've got the right answer is to type this statement into your calculator and type our answer into your calculator and confirm that they are the same significant figure. All right, that's question 1. Let's go on to 2. So in question 1, we did a question from 7b, we did a question from 7c. So we did, integrating to the inverse trig functions. We've done some substitution. Now it says specifically, use integration by parts to show that. And it wants us to integrate the integral of x sine 2x with regards to x. So I'll write the formula up again quickly. It's the integral of u v dash is equal to u v take the integral of u dash v. Okay, that's the form for integration by parts. And so we need to first identify what corresponds with u and what corresponds with v dash. Now remember, we want u to be easy to differentiate and v dash to be easy to integrate. In this case, both of them satisfy it. However, it does have to take a particular order. If you try, let's put both up here and show you that one of them doesn't work. Okay, V and V dash. All right, so if we do U is sine 2x, then U dash will be 2 cos 2x. And then we would have V dash is x, and the integral of V dash is going to be x squared on 2. Now the problem with this is that we'll have UV, okay, U times V, that's fine. Take away the integral of U dash V, and all of a sudden we still have some x squared component multiplied by some trig component, which we would have to perform integration by parts to solve. We don't know how to integrate a product apart from integration by parts. So that means we have to swap the order around. So I'm going to have U is x, U dash is 1, V dash is sine 2x, and the integral of sine 2x will be negative half cos 2x. Okay, so when we smash those together then, we'll have UV, so I'll just write out the whole thing, integral of x sine 2x is equal to UV, that's going to leave us with minus half cos 2x. Take away the integral of U dash V. So now we have 1 multiplied by some function. All right, and that's nice and easy for us to integrate. That gives us plus a quarter integral of cos 2x sine 2x. Plus the, all right, which is exactly what they've stated for us. A quarter sine 2x, take half of cos x cos of x. Why am I missing an x?
U dash V, not UV.
Very good. Excellent. Okay, so on to B then. And we're given the graph of the function x sine 2x. It looks like this. And we've got here that this is pi on 2, and this is pi. Okay, the figure below shows the graph. Show that the area below the x-axis is 3 times the area above the x-axis. Okay, so what we're required to show is that the integral from 0 to pi on 2 is equal to 3 lots. 3 lots of the integral from 0 to pi on 2 is equal to the integral from pi on 2 to pi. So firstly, let's just evaluate both of those separately. So if I go the integral from 0 to pi on 2 of x sine 2x. Okay, we've already performed the integration by parts, so we know what it integrates to. We'll just apply the fundamental theorem of calculus straight away. And like a good way to communicate this, like you can just do it like that, but I reckon if we go, you know, we define area A and area B, and we talk about, well, area A is going to be equal to this integral, area B is going to be equal to this integral, and therefore we can finalise the relationship between A and B. Okay, x sine 2x evaluates to x, so I'll write it out the way they've got it, a quarter sine 2x, take x on 2 cos x, cos 2x. We don't need plus c because we have a definite integral. Okay, and then we're plugging in our upper boundary. 2 times pi on 2 just leaves you with pi. And then we're going to have pi on 2 on top of 2, equals pi. Okay, so that's the upper boundary. When we put the lower boundary in, sine of 0 is 0, so that part's 0, so we'll just focus on this part. We have 0 multiplied by 1, so that's just going to be 0 as well. So we can just go, that component's going to be 0. Okay, sine of pi is 0, so we're focused here then. We have minus pi on 4 times minus 1. That leaves us with positive pi on 4. So we've got the integral statement, the definite integral, the substitution, and our answer. Okay, so that's the area for region A. Let's do it for region B. B. equals, and we're going to have the integral from pi on 2 to pi of x sine 2x and we'll just keep processing here. First component, and I'm just going to write subtraction underneath it because I don't have enough room there. And it's going to be the same as this one, isn't it? What sine pi, take pi on 2, on top of 2, cos pi. Okay, slowly evaluating that, component's going to 0. Here we've got minus pi times cos of 2 pi. Minus pi times cos of 2 pi, that's a negative value. So we're left with minus pi times positive 1. Minus pi, take away, that component's 0. This component's going to be negative pi on 4. So negative pi on 4. Leaves us with just one lot of negative pi on 4. And so when we combine those together, negative 5 pi on 4. Why is our answer negative?
Because it's under the x-axis, is that it?
Correct, yeah. It's because it's below the x-axis. Right. I think when I copied this question yesterday, I think our answer's correct. I think the question's wrong when it says 3 times. Let's just check on the calculator, otherwise we've made an error in here somewhere. So let's go from pi on 2 to pi of x sine 2x minus 3 pi on 4. I think I might have messed up the negatives. No, negative and negative make it positive. Negative. Well, we've got minus 5 pi. Minus 4, take 1. What's going on here? That component's, yeah, pi on 4, and then we have that negative. Yep. So what about this component then? That's 0, that's pi, minus pi, times, yep, that's minus pi. And we know, once we've evaluated it, it has to be positive for area. Can anyone see what's going on there? Pi on 2 to pi, x sine 2x. That's a lot of the other one. X sine 2x. Yep, so that's correct. This isn't for some reason, it should be 3 pi on 4. Missing a negative. I'll spin it around and I'll have a look in a moment. Let's do the last one. So just like, and maybe that's some good advice for you here. Okay, you're in a test, you've got a problem, all right, we haven't reached the answer verified. Do not get bogged down. Because right now, like as that stands, don't have the right answer, but I've shown at least 3 out of 4 marks, right? And so you could spend another 10 minutes trying to find where the error is there. It's not worth your time. The best advice is get as many marks as you can for it. We've done some there. Let's move on to the next question. All right, find the exact volume when the function y equals 2x plus 1 from 0 to 4 is rotated around the A, the x-axis, and B, the y-axis. First thing I'm going to do is just sketch this function. 2x plus 4, so it has a y-intercept of 4 and a slope of 2. It's the equation of a line, and we're integrating the first calculation for the volume is we're rotating it around the x-axis. Okay, so this is, it's going to be like, what would you say? It's most of a cone. Okay, it's like a cone but cut down the middle without the pointy end. Okay, so for volume around the x-axis, we have volume is equal to the integral from a to b of pi times f of x squared. Okay, so in our circumstance, we're integrating from 0 to 4. Our function is 2x plus 4 and squared. Now, this is a pretty basic integral calculation. I think the skill involved is drawing out the skill for us is drawing out the going from here to here, basically. Not too challenging when we're rotating around the x-axis. The other thing is we do need to apply a perfect square before we integrate that, or you can integrate it as ax plus b to the n. Yep.
Is the equation 2x plus 1 or 2x plus 4?
What's the sheet say? Oh, plus 1, sorry. Yeah. There you go, 2x plus 1. So y-intercept of 1, slope of 2. Yeah, so perfect, if we perform perfect square expansion first before we integrate it. We can even pull pi out the front, that simplifies our fundamental theorem of calculus. Okay, we'll have a squared, so 2x squared plus 2 lots of a, b, plus b squared. Okay, that's perfect square expansion, and then you're ready to integrate step by step. Give us integral of 4x squared is going to be 4 on 3, x to the 3. Plug in the 4. Okay, we know when we sub 0 in, because every component is a product of x, it's going to evaluate to 0. And then, all right, we'll type in our answer. Again, doing things quickly, you type this statement in your calculator. Don't type this in, that takes too long. It's too easy to make an error there. We just type in our statement here. Anyone done it yet? Race here. 2x plus 1 from 0 to 4, 20 times pi. Oh, I didn't square it either. Shift pi, 2x plus 1 squared. 364 on top of 3 pi. So there's our answer expressed exactly. Very good. Okay, now what we're going to do is rotate the same function around the y-axis. So, any questions about that one, by the way?
Squared, so you're just writing 2x squared.
Yeah, you can write 2x squared, that's fine. I just didn't simplify it.
So I didn't get 364
I just typed that in.
Okay.
So yeah, we'll come have a look at your answer in a sec. But yeah, so what I've written here has to be the answer. Error is occurring when we're trying to simplify things and stuff. All right. Okay, so if we're rotating around the y-axis, we've got the same function, but now we've got to think of it like I'm rotating this one around here, and this one's going here. So this one definitely is a cone. We've got a straight edge. In fact, you could probably use a cone. You can use a cone formula to calculate the volume, but we're using integration techniques at the moment. All right. So the integral when we're rotating around the y-axis is the integral from c to d, where c is the lowest y value and d is the highest y value. So our lowest y value then is 1, and our highest y value is when x is 4. What's the y value? 2 times 4 plus 1, isn't it? The equation is 2x plus 1. So that means we're integrating from 1 to 9. And we need it expressed as a function of y, don't we? Sorry, not a function of x, a function of y. So if we have y equals 2x plus 1, we're going to express it as a function of y. We're going to rearrange to get x by itself, aren't we? We have x equals. So the first thing to do is subtract 1 from both sides, and then divide both sides by 2. Okay, that's our function of y. And so that means our volume calculation then is going to be the integral from 1 to 9 of pi times our function of y squared. With regards to y. And this one we'll just type straight into our calculator, as we've done lots of integrals. And again, that's a perfect square expansion. Then you're integrating term by term, but with y instead of x. Fundamental theorem of calculus, get yourself an answer. I'll leave that for you guys to have a go at if you want. So we have pi, and then we have 0.5 x take 0.5 from 1 to 9. 16 then square it. 128.35. All right. I'm going to pause and flip. Okay, so my error has just occurred here when I've subbed in pi. Okay, so pi is going here, we get 2 pi. Pi is going here, we get pi on top of 2, not 2 pi on top of 2. So that's where it made an error. So that term then is minus pi on 2. Take away pi on 4, gives you minus 3 lots of pi on 4. Now our answer is negative because it's below the x-axis, but the magnitude of the area we can see is 3 times that of b. So to communicate your answer, like we've shown all the mathematics we need to, but we might just say a equals pi on 4, b equals 3 lots of pi on 4, therefore a equals 3a equals b. All right. Cool.